Welcome. You know, if you've ever gotten your hands dirty with Cisco ACI, you know it's all about policy. But have you ever stopped to wonder how the fabric actually enforces those security rules deep down inside? Well, today we're going to pull back the curtain and decode that security blueprint by focusing on one of the most critical pieces of the puzzle, the policy control tag, or as we'll call it, the pcTag. So let's start with the big question. Imagine you've got this complex ACI fabric, right? You've built out your tenants, your VRFs, your application profiles. You've drawn all those nice little contract lines between your EPGs. But when a real packet actually hits a leaf switch, what is it? What's the mechanism that makes the final call? Permit or deny? How does that abstract policy you drew become a hard and fast rule in the hardware? Well, the answer to all of that, as you're about to see, comes down to the pcTag. All right, so here's our game plan. First, we'll nail down exactly what a pcTag is. Then we're going to dissect something called a zoning rule to see how these tags are actually used in the real world. After that, we'll get practical and I'll show you how to find these tags and their scopes using both the GUI and the CLI. And finally, and this is super important, we're going to talk about a critical real-world problem, policy TCAM exhaustion, and look at some key strategies to make sure you never run into it. Okay, let's get right into it. Seriously, the entire ACI security model is built on this one simple but powerful concept. If you can understand the pcTag, you're well on your way to mastering ACI policy. So what is it really? Well, a pcTag, and you might also hear it called a class ID or an S-class, is really just a number, a unique ID. Every single time you create an EPG, the APIC assigns it one of these numbers. Think of it like an identity card for that EPG inside the fabric. So when you create a contract between, say, your web EPG and your DB EPG, you're not actually telling the switch to connect those names. Nope. You're telling it to create a rule between their underlying pcTag numbers. And that is how the abstract policy gets translated into something a piece of hardware can actually understand and enforce. Now, as you can see here, not all pcTags are created equal. They fall into a few different ranges. The first couple, 1 through 15, those are reserved for the system, so we don't touch those. The really important distinction for us as architects is between global and local tags. See, by default, when you create an EPG, it gets a local pcTag. That means the number is only unique inside its own VRF. And most of the time, that's totally fine. But what happens when you need to share a service, like a firewall or a load balancer, across different VRFs? Well, for that to work without conflicts, ACI automatically promotes the provider EPG's tag to a global pcTag. That makes it unique across the entire fabric. Remembering this is absolutely key for any shared service design you do in ACI. Okay, so now we know what a pcTag is. Let's see how it's actually used to build the security rules that get programmed into the switch hardware. These are called zoning rules. Believe it or not, every single policy decision in ACI boils down to a rule made of these 5 ingredients. You've got the source pcTag and the destination pcTag. That's the who is talking to whom. You've got the filter ID, which defines the protocol, and port. That's the what they're allowed to talk. Then there's the scope, which is just the VRF's unique ID. That tells us where this rule is valid. And finally, you have the action, usually permit. These 5 little pieces of information make up one single entry in the hardware. And check this out. This shows you exactly what those rules look like in the real world. This is the output from the show zoning rule command on a leaf switch. And you can see the columns line up perfectly with what we just talked about. See? SRC EPG and DST EPG. Yep, those are our source and destination pcTags. You've got filter ID, which is the traffic type. And you have scope. In this case, that big number, 2523163, that's the unique ID for our VRF. This isn't just theory anymore. This is the actual physical policy that's been programmed right into the silicon. So in that last screen, you probably saw all those filter IDs, just numbers like 17, 18, 19. But what do those numbers actually mean? What specific kind of traffic are they allowing? To figure that out, we've got to drill down a little deeper. And we do that with the show zoning filter command. If we pop in the ID number, we can see exactly what's inside. So here for filter ID 18, it's actually 2 different rules. One for ICMP, which is ping, and another for TCP on destination port 22, which of course is SSH. This is how you trace a high-level contract from the APIC all the way down to the specific protocol and port being allowed on the hardware. This is a must-have troubleshooting skill.
All right, so we've seen all this great info on the leaf switch CLI, but as an administrator working in the APIC, how do you find these pTags and scopes for yourself? Let's take a look at how to do it in both the GUI and the command line.
Okay, the easiest way, by far, is right in the GUI. Just navigate to any EPG you want, click on the Policy tab, and then the General subtab, and boom, right there in the Properties, you'll see the PC tag listed. In this example, our app_EPG has the tag 16932. It's really that simple.
Now, for all of you who live on the command line, or if you need to automate things, the MOQuery command is going to be your absolute best friend. By querying the FVAPG class and filtering by the name of your EPG, you can pull up the exact same information. So here, we query for our app EPG, and what do we see? The PC tag attribute is 49154. It just goes to show you there's perfect parity between what you see in the GUI and what you can get from the CLI.
And finding the scope, which is that unique number for the VRF, follows the exact same pattern. In the APIC GUI, if you look at the VRF's policy tab, it's called the segment ID. Over on the CLI, if you run a MOQuery for that VRF object, the same number is listed, but this time it's under an attribute called scope. Let's look at them side by side. And here we go. On the left in the GUI for our pre-sales VRF, we can see the segment ID is 2523136, and on the right in the MOQuery output for that same VRF, the scope attribute is, you guessed it, 2523136. It's the exact same number, just with a different label depending on where you're looking. And this is the number that gets programmed into the scope column in those zoning rules we saw on the leaf. Now here's a fantastic power user tip for you. If you ever need a quick audit of all the PC tags and scopes that have been assigned inside a tenant, there's an amazing dashboard for it. Just navigate to the tenant, click on the Operational tab, and then Resource IDs. This screen gives you a beautiful, clean table of all your EPGs, their assigned class ID, or PC tag, and the scope they belong to. It is an incredibly useful view for checking your work and for troubleshooting. So far, this all seems pretty slick, right? But there's a hidden cost to all this powerful, flexible policy enforcement. And it's a critical hardware limitation that every single ACI architect absolutely needs to understand. This quote from the documentation really says it all. The TCAM is a specialized, super high-speed type of memory on the switch hardware, where these zoning rules get stored. The key phrase here is important system resource, which is a nice way of saying it is finite. It's not like your computer's RAM or a hard drive. You can't just pop in some more. So here's the bottom line. Every single contract you apply and every filter inside that contract creates zoning rules. Each one of those rules takes up one slot in that policy TCAM. So if you have a really complex environment with hundreds of EPGs and all kinds of crazy contracts, you can literally run out of space in this hardware table. And when that happens, the fabric can't program any new policies, and that can lead to major connectivity failures. This whole problem is known as policy TCAM exhaustion. So how do we avoid this ticking time bomb? Well, thankfully, ACI gives us several tools and design patterns to help manage this precious TCAM space. Let's walk through the main options. There are really three main strategies to think about. The most, let's say, blunt approach is setting the VRF to unenforced. This basically turns off contract enforcement within that VRF, making it act like a traditional network, where everything can talk to everything. This consumes zero policy TCAM entries. For more fine-grained control, vZANI is amazing for shared services. Instead of having hundreds of EPGs all pointing a contract to a single firewall, you just apply one contract to everything. Finally, there are contract-preferred groups. These are really useful for creating tiers, like a production group and a development group, where everything inside the group can talk freely, but to talk between groups, you still need a contract. All of these are tools in your belt to build smarter, more scalable designs. And that really brings us to our final thought for today. Now that you understand how policies are built from pcTags and how they get translated into zoning rules that consume real finite hardware resources, it's worth asking yourself, is your own ACI policy deployment as efficient as it could be? Or could that complex web of contracts be slowly, silently building towards a TCAM exhaustion event? Knowing what to look for is always the first step. Thanks for joining me.